Hi everybody. This video is going to be on section 4.3, which is subspaces. So let's start with a definition. Let S be a non-empty subset of a vector space V over F. Remember, F is just the scalar field. In other words, it's usually the real numbers or the complex numbers, but we're just going to write over F. By the way, when we talk about a non-empty subset, an easy way to write this looks like this. We can say we want a non-empty subset of V. This is how we would write it, okay? That's a symbol that means the same thing. So if this subset S is a vector space itself, so is itself a vector space over F under the same vector addition and multiplication. Oh, sorry, I should have said and scalar multiplication, just to clarify here. And scalar multiplication as V, we call S a subspace. Subspace of V. Okay, so if we have a subset that is non-empty and is itself a vector space, in other words, all 10 of those axioms are true with this subset, then we call it a subspace of V. So informally, you want to think about it as follows. A subspace of a vector space is a subset that preserves the structure, and we'll put that word in quotes here. Obviously, that's the informal part of what I'm writing. Preserves the structure of the vector space. Okay. So out of this comes a question. The question is, if we have a non-empty subset S of V, do we need to check all axioms of S to show it is a subspace? Okay. Well, lucky for us, the answer is no. All right, and that's given to us by the next theorem. So theorem. let V be a vector space. And suppose that we have a non-empty subset of V. Then S is a subspace if and only if S is closed under vector addition and scalar multiplication. In other words, all you need to do really is check axioms 1 and 2. You get all the other 8 axioms for free if we're dealing with a subset of a vector space. Okay. Very neat fact. So that gives us a big, nice shortcut for showing something is a subspace. Note something to keep in mind here before we go on. It is very helpful to use set builder notation for defining a subset of V. So the way it works is it looks like this. You say the set of all V in V such that some property holds. Many times that we're going to define subsets this way, okay? Okay. So let's go ahead and do an example, okay? Let's let S denote the set of all real solutions to the linear system below. So this is our system, x1 minus 4x2 plus 6x3 is equal to 0. Negative 3x1 plus 10x2 minus 10x3 is equal to 0. Express S in set notation and verify that S is a subspace of V. Okay. So how do we do this? Remember, well, let me start with the first part here, okay? It says express S in set notation. So here would be the easiest way to put this in set notation. I'm going to let A be the matrix that corresponds to the system, the coordinate or coefficient matrix, 6, negative 10. And then we know that 0 is defined as 0, 0. And let's suppose that X is equal to X1, X2, X3, right? Our solution, or our solution set. And so if we write it that way, then that means we can write S in set builder notation. Remember, let's look back up here. It says S denotes the set of all real solutions to that system. Well, what does this system become now? This system becomes A times X is equal to 0, right? Because the B vector is 0. So S is going to be the set of all X in what? In R3, isn't it? These are three-dimensional vectors such that A times X is equal to 0. That's how we define the set. By the way, in my original problem, I said verify that S is a subspace of V. Let me actually write down what vector space we're talking about, of course. We're talking about R3, right? So verify that this subset S is a subspace of R3. Okay. So how would we do this? Remember, we need to check that the axioms hold for all elements inside of S, but we only have to check the first two axioms, okay? So let's check A1 first. So let's take any two vectors inside of S. In other words, we're supposing that these two vectors live inside S. That means that A times x1 is equal to 0 and A times x2 is equal to 0, right? Because by our definition of S, they must satisfy this property. But what would A times x1 plus x2 be? Well, we know the way that matrix multiplication works, that it distributes over addition. So this means that this is equal to ax1 plus ax2. But by above, each of these, I'll underline it in red, each of those is equal to the 0 vector by assumption, right? So that means that this is going to equal the 0 vector plus the 0 vector, which is just the 0 vector. So what did we just show? We just showed that A times that is equal to that. And so that means we've just showed that x1 plus x2 lives inside S. And so that is the first axiom. So that's axiom A1. How about A2? Let's let K be a real number, and let's take a vector that lives inside S. Okay. Remember, this means that A times X is indeed 0. Now remember, we're trying to show that this is true. If you multiply K times X, you still get something inside of there. So what would A times KX equal? Well, we know by the property associativity of scalar multiplication, we know that this is equal to Ka times X, because the scalar pulls out. And we know that's equal to K times AX, again by associativity. But that's just K times the 0 vector, which we know is the 0 vector. Okay, and so since this guy, when you multiply it on the left by A, gives you 0, then this means that Kx is in S. So what did we just show? We just showed that axiom 1 and axiom 2 hold. So in particular, this shows, let me just write this down. This shows that S is closed under vector addition. And this shows that S is closed under scalar multiplication. Now, perhaps more important than either of these things, I do need to be careful. I'm not quite done with the problem because I need to make sure I specify that S is non-empty. Why is S not empty for sure? How do we know that something lives inside of here? Because this is important. What if this system has no solutions, right? We can't have a subspace that's defined by all solutions if there are no solutions. So how do we know that there are solutions to this system? Well, you can just see one, right? The solution to this, the zero vector, clearly solves it, doesn't it? We know that that's true when you have a homogeneous system. Okay, so let's put that here. Let's put it, in fact, at the very top. Note, S is not empty since the zero vector lives inside S. Right? We know that A times zero vector is equal to the zero vector. So, that's good. Okay? So what did we just show? We just showed, therefore, S is a subspace of R3. Okay? That's how you show something is a subspace, right? All you have to do is show that axiom 1 and axiom 2 hold for all elements in S. Okay. So let's keep going here. We've just shown how you show that something is a subspace. So how would you show that something is not a subspace? That's a little bit easier, I think. I should say it's easier because there's less work to do. So let's verify that. We're going to do a brand new one, okay? How about the set of all x in R2 such that x is equal to r comma negative 3r plus 1, where r is in R. Verify that that subset is not a subspace of R2. Okay. All right, so how do you show that something is not a subset? Or sorry, not a subspace. To show something's not a subspace, you have to find a counterexample to one of the axioms. If you can show that one of the axioms does not hold, then you're good to go, right? So let's do this the easy way here, right? If R were equal to 0, then this means that 0, 1 is inside of S. So we know it's not empty. And if R is equal to 1, then that means the vector 1, negative 2 is inside S, right? I guess we don't even need what I just wrote down to show what I'm about to show, okay? So remember, if it is a subspace, then that means it needs to be closed under scalar multiplication. But what happens if you multiply this vector by the scalar 2? This would equal 0, 2, and 0, 2 is not inside of S, right? How do we know? Because it doesn't equal 0, comma, negative 3r plus 1, right? It does not work. Okay. What does this mean? This means S is not closed under scalar multiplication. Another way to put that is A2 fails. Okay. What does this mean? This means S is not a subspace of R2. So as a tip here, this is important to show something is not a subspace you only need to find one axiom counterexample. Think of it this way. If somebody made a claim that all sheeps are white, how would you prove them wrong? All you need to do is find one single sheep that's not white, and then that disproves their claim, right? So if we want to show that this thing is not a subspace, all we have to do is find one single axiom of vector spaces that doesn't work. So you just have to look at it and think about the definition and think about what would fail about being a vector space. Okay. Something useful to check, by the way, is called the zero vector check. So we have something called the zero vector check. This is one of the easiest axioms to disprove. It says if, obviously, how would you disprove the zero vector? So if the zero vector is not inside S, then S can't be a subspace. Now be careful, of course, the counter to this, the converse, is not necessarily true. So in other words, if you check and 0 is inside S, S may or may not be a subspace. In other words, you don't get any information, right? Okay. All right, so let's try another example here of showing that something is a subspace here. So, example. Let's let S denote the set of all real Skewsymmetric n by n matrices. Verify that S, which is contained in there, is a subspace. And for those of you that don't recall, this is just this guy right here. Remember, this is the vector space of n by n real matrices. So we already showed, if you recall, that the set of n by n real matrices do form a vector space. What we're trying to show now is that this subset, okay, which is all real Skewsymmetric n by n matrices, we want to show that that is also a subspace. Okay, so let's first start by defining S in set builder notation, okay? So what would it be in set builder notation? So S would be the set of all matrices that are n by n such that their transpose is equal to the negative of itself. Remember, that's the property. That's what it means to be skew-symmetric. And so we want to show both axioms here. So let's start by looking at axiom 1. Remember, we want to show it's closed under vector addition. So let's take two guys that are inside of S. We want to show that their sum is in there, right? So Remember, this means if these are both in there, then that means that A1 transpose must be negative A1 and A2 transpose must be negative A2. So what would A1 plus A2 transpose be? So let's think about transpose. We know that transpose does distribute over addition, right? That's something that we learned when we looked at transpose earlier on. So this would be A1 transpose plus A2 transpose, which we know by what we wrote above that this is equal to negative A1 plus negative A2, but we know that that's equal to negative A1 plus A2. So what did we just show? We just showed that A1 plus A2 transpose is equal to negative A1 plus A2. Doesn't that mean that A1 plus A2 lives inside of S? Because everything that lives inside of S is skew symmetric. And so we just showed that there's some, that its transpose is equal to its negative. So what does this mean? This means that A1 holds, right? Axiom A1 holds. It's closed under vector addition. Okay. So now let's look at axiom A2. Let's let K be a real number. And let's also let A be in S. Remember, this means that its transpose is equal to its negative, right? So now we want to show that the same thing is true for K times A. So what is K times A transpose? Well, K times A transpose. Okay, so if you multiply a matrix by a scalar and then you do the transpose, we know that that's true, or that's the same thing as doing the transpose and then multiplying by the scalar. We know that's true. But that's just equal to K times negative A because of the property that we wrote above it. And so this is equal to negative K times A. Again, this is just how scalar multiplication works. And so what did we just show? This means that Ka is in S. In other words, axiom A2 holds. So what does this mean? Well, one more thing, we do need to show, and well, we know that this is a non-empty subset, right? I mean, the zero vector is in there, so it's definitely not empty, right? We know that S is clearly not empty. And so S is a subspace, right? Because we only need to check those two axioms. Cool. So we finished another example. Let's do another one. Let's take R2. Let's let S1 equal the set of all x minus 1 such that x is a real number, and let S2 be the set of all vectors of the form x squared such that x is a real number. Show neither S1 nor S2 is a subspace of V. Okay, let's start with S1. Look at the construction of S1. Notice that we have x comma x minus 1, right? For example, things like 1, 0 would be in there. Or 2, 1 would be in there. Or pi minus 1 would be in there. So what's the easiest way of showing that this cannot be a vector space? Well, how about we do the zero vector check? Can the zero vector be in there? No, because 0, 0 cannot be inside of S1. And the reason why is that if 0, 0 were in S1, then that would mean that this would have to be x, and this would also have to be x minus 1, which is impossible, right? It's not possible. Not possible. So that means we're done. S1 is not a subspace. It fails the zero vector check. Okay. What about S2? Let's look at S2. Now, sadly, in this case, 0, 0 is inside of S2, isn't it, right? Because look at the way S2 is defined. S2 is defined as being, you just take the first coordinate and you square it, and that gives you the second coordinate. So certainly 0 squared is equal to 0, right? So let's write that down. Since 0 squared is equal to 0, right? Okay, so that's not going to work. But remember, that doesn't mean it is a subspace. It just means we can't use this to disqualify it, right? So what's an easy way to do this? Well, let's take 1, 1. 1, 1 is inside of S2, isn't it? How do we know? Well, because 1 squared is equal to 1. Since 1 squared equals 1. But now let's multiply it by 2. 2 times 1, 1 is equal to 2, 2. But 2 squared is equal to 4. So what does this mean? This means that 2, 2 is not in S2. And so what did we just show? We just showed that axiom A2 fails. It's not closed under scalar multiplication. And so this gives us that S2 is not a subspace. S2 is not a subspace. Again, all you need to do is find one single counterexample. So my counterexample was vector 1, 1, right? We know that if something's in there, it's got to be closed under scalar multiplication, and clearly it was not. Obviously, there's many ways you could have approached this problem, but that's just the way that I chose to do it, okay? Okay, let's do another example. Let's let V be the vector space of all real valued functions defined on an interval A to B. And let's let S be the subset of all functions that live inside V such that f of A is equal to f of B. In other words, all functions that equal the same number when you apply it to A and B. Okay? Show that S is a subspace of V. Okay. So, first of all, of course, this guy is not empty. So, note, S is not empty since, you could just take any constant function, right? Any constant function lives in S. Right? For example, if we took the function where f of x is equal to 1 for all x, then certainly f of A is the same as f of B, right? They're both 1. And so obviously S is not empty. So now let's look at the two axioms here. Let's look at axiom A1. So let's suppose that F and G both live inside S. And remember, we're trying to show that this is closed under addition. So, first of all, this means that f of A equals f of B and G of A is equal to G of B, right? This is what it means for f and G to both live inside S. And now we want to show that f plus G of A is equal to f plus G of B. So what's f plus G of A? We know that f plus G of A is defined to be f of A plus G of A. Okay, but because f of A is equal to f of B and G of A is equal to G of B, then this means that this is just equal to f of B plus G of B, which is equal to f plus G of B. In other words, A1 holds. Okay. What about axiom A2? So let's take any real number and let's also take an f to live inside of S. So remember, this means that f of A is equal to f of B. So what would kf of A equal? Remember, a constant times a function is the same as just taking the function of the number and then multiplying it by the constant. So we know that this is equal to k times f of A. But that's just k times f of B by the property we're assuming above. And so that's just equal to kf of B. And so this means that A2 also holds. Okay. And so this means that S is a subspace. Okay. There we go. So let's do a couple of theorems and definitions here that we're going to need, okay? So does every vector space always have a subspace? Well, this next theorem will tell us yes. Let's let V be a vector space. And let's let S equal just the zero vector. That's it. then S is a subspace. That's what our theorem says. In other words, if you just put the zero vector inside of a set, that is its own subspace. Note, we call S the trivial subspace. Not a very interesting subspace, right? It just has 0 in it of V. Okay, so this is so simple that we're actually going to prove it. So what would the proof be? Well, if you're just the zero vector, this means all we have to do is check that axiom 1 and 2 are true for the zero vector. Well, what's the zero vector plus the zero vector? It's equal to the zero vector. And what's the constant times the zero vector? It's also equal to the zero vector, and both of those live in S. In other words, A1 holds and A2 holds. So we're done. Very easy proof. Okay. Let's do another more interesting problem here. Let's do a theorem, a more interesting theorem. Let A be an m by n matrix. The solution set of the homogeneous system of equations AX equals 0 is a subspace of Cn or Rn if the solutions are real. Okay, that's nice. So for any m by n matrix, the solution set of the homogeneous system of equations that we get is a subspace. So what's the proof of this going to be? Well, how about just seeing example 1? So see the first example of this section. If we go back to the first example of this section, didn't we have a homogeneous system of equations? And I asked you to to check that all the real solutions formed a subspace. So why did it work? Well, it worked because we were able to check the axioms here, and you notice it didn't even matter what A was. We never used the actual numbers that made up A, did we? Right? These are the numbers that made up matrix A, but we didn't even care because when we did the problem, we did it for A in general. In other words, we really proved it was true for any homogeneous system of equations. So the solutions of a homogeneous system always form a vector space. This is going to be extremely useful later on when we go back to solving differential equations. So remember this. This will be important later. In fact, I'm going to write that down here. So this is so this theorem is very important result. We're going to use it a lot later. All right, so in fact, this is because for any matrix, this forms a vector space, we give it a special name. So, definition. We have something called the null space. So let's start actually, you know what? Let me back up for a second. Let's let A be an m by n matrix. The null space of A, null space of A, is the solution set of the homogeneous system Ax equals 0. Yeah. There we go. So another way to define it is like this. The null space of A is equal to the set of all x in Cn or Rn. It just depends on whether the solutions are real or not, but certainly they live in Cn no matter what, such that Ax is equal to 0. Okay, that's how you define the null space. Okay. We're going to do one more example. Let's let V denote the vector space of all real-valued functions defined on an interval I. And let's let c to the k of I. So what does c to the k mean? This just means, well, I'll tell you. Let c to the k of I denote the set of all functions in V that are continuous and are at least k times differentiable. This just means that you can take the derivative of the function k times, right? The first derivative exists, the second derivative exists, and you can do this as many times until you get to k, whatever k is. So where k is some natural number. Okay. We want to show that c to the k is indeed a subspace. Okay, so how do we do that? Again, we need to show that both of the axioms hold, the first two axioms of a vector space, right? Okay, so let's start with A1. Okay, so A1 first. Let's start by taking two functions inside of c to the k of I. Oh, you know what? Right here, I should have said c to the k of I, right? There we go. c to the k of I is the whole name. So let's take two functions in there, right? Okay. So what does this mean? This means, since they're both in there, that f and g are both continuous and k times differentiable. That is the definition of what it means to live inside that set. So they're continuous and k times differentiable. But what do we know by calculus? In calculus, you learn that if you have a derivative, then that means the sum of the two functions have a derivative, right? The sum of two differentiable functions is differentiable. So by calculus, f plus g is also continuous and k times differentiable. So what does this mean? This means that f plus g lives inside of c to the k I, or in other words, a1 holds. Okay. Also, if k is any real number and f lives inside of c to the k I, certainly multiplying the function times a constant is not going to change whether or not it has a derivative, right? So kf is also continuous and k times differentiable. By calculus. And I say by calculus because I mean we already know this from having taken calculus, right? So this, of course, is A2, right? This means that A2 holds. Because this means that k times f is in c to the k I. So c to the k I is a subspace. And so, just to write one last thing down, we've talked about a lot of different vector spaces here. So let's write down a summary. What is a summary? Actually, let me do this on the next page, okay? So we're going to write down a summary of important vector spaces that you should know. So Rn, that's an important one. Cn, that's another important one. So what are some more? We know that all m by n matrices with real coefficients, that's a vector space. We also know Mn of R, all that means is n by n matrices, right? With real coefficients. What else? We also know that Pn of R. Remember what those are? Those are all polynomials with real coefficients of degree n. We know those form a vector space by the last section. And we just learned about this guy, c to the k of I. Also, the null space of a matrix. And we also know the functions on an interval I. So these are some important vector spaces whose names we should know because we've been looking at these examples over the last few sections. Okay. Remember, another word for null space of A are the solution set of homogeneous systems of equations. So the null space of A does have kind of a deeper context to it. Just don't forget what the definition of all these things are. Keep all of them in mind because they're going to be the tools we work with throughout the following sections. Okay, everybody, that's it for this video. Thank you so much for watching. See you on the next one.